Hi guys, this is Mr. Adams from Midwood High School, and I hope everyone is staying safe. We're moving into a new topic called oxidation and reduction, and what I'm going to do in this video, I'm going to give us a little bit of a introduction as to what oxidation and reduction is. Okay, now the thing is, oxidation and reduction, right, is a very, very, very important topic in chemistry. It also is a foundation for a topic that we're going to do later on called electrochemistry. I'll send you guys a video later, so you're going to watch that. And in this video I'm doing right now, and the other one I send, please take detailed notes, okay, with the rules and examples, okay, because this video has some rules that are very, very important. Alrighty. Now, in terms of oxidation, right, from its name, what do you think it involves? All right, so oxidation, oxy. Okay, we're thinking about oxygen, right? Now, oxidation reaction, right, takes place in a lot of different things in our lives that we see or experience. For example, every time a cop pulls someone's over and checks them with a breathalyzer, that's an oxidation reaction. Anytime you're burning wood, for example, oxidation or redox takes place. Okay, and also when we have rusting or corrosion, that's also oxidation and reduction taking place. Alrighty. We use the term redox, okay, in this topic. The reason being oxidation and reduction cannot take place without each other. Okay, they happen simultaneously together. So yeah, we use the term redox, no problem. Alrighty, now we're not going to copy anything on this page, but just as a historical perspective, if a reaction took place, right, and you produce some type of oxide, okay, that was called oxidation. And if it took place again, another different reaction, and you produced oxygen, okay, that was called reduction. All right, so you're losing or giving up oxygen, that's called reduction. But we're not going to use these definitions. That's just a bit of historical perspective. Okay, so the thing is, guys, what do you think is being lost or being gained in this topic of oxidation and reduction? Okay, now if you guessed electrons or knew it was electrons, you're absolutely right. Okay, so electrons are key. Alrighty. Now I want you to take information down from this page. All right. Now here's the deal. This guy right here is very important. Okay, this is our first important definition. Oxidation occurs when a substance loses electrons. Okay, so make a note of that. Oxidation occurs when a substance loses electrons. And once again, guys, when a substance loses the electrons don't disappear like, in the Twilight Zone. Something else will gain them, right? So when a substance gains electrons, okay, that's called reduction. Okay, so we have oxidation and reduction taking place simultaneously there. Now, there's a memory device for these two terms. We have Leo and we have Ger. So what do you think Leo means? Okay, Leo means loss of electrons, oxidation. Ger means gain of electrons, reduction. Okay, now there's also oil and ring, right? So if you have, you can say oxidation is loss and reduction is gain. And we're talking about electrons here for oil and rig. So either one, whichever one you like, use it, no problem. Now, this experiment right here, guys, I would have done this in class with you guys. I've done it already, I think, with you. But I love this experiment because you can explain so many different concepts with it. It's when I react magnesium ribbon with oxygen. And remember, it's very, very, very exothermic and very bright, right? Now, the thing is, what I want us to look at, guys, is I want you guys to do me a favor. I want you to find your reference tables, right? Okay, find your reference tables, all right, and check out the valence electrons. How many valence electrons does magnesium and oxygen have? And also check out the electronegativity of those guys. And based on the number of electrons, valence electrons, and based on the electronegativity, how do you think those electrons will behave? All right, so think about that for a second. Okay, so we see here, right, in this reaction, right, we have magnesium here and we have oxygen, right, and they're reacting with each other to give magnesium oxide over here, okay? All right, put a little 2 in front there to balance it. Okay, so we know from experience, if you look on your reference tables, right, magnesium's electron configuration, right, is 2, 8, 2. Now we're going back to Chem 1 here, right? And these are two valence electrons right here. So we know from experience, right, if magnesium and metals want to be stable, they will tend to what? They will tend to lose their electrons, lose their valence electrons. And when those valence electrons are lost, right, okay, they don't go into outer space, but oxygen is going to gain them. Okay, so when he loses two valence electrons, that are these two blue valence electrons up here, okay, his configuration now becomes what? It becomes 2-8, right? And if you have 8 in the outer shell, you're now stable. Now let's look at oxygen. Okay, now oxygen, okay, its configuration is 2-6, right? Now, if he gains 2 more electrons, okay, his configuration will become what? Will become 2-8, okay? So now it's 2-8 on both levels, and they both have the configuration now of neon, right? Noble gas configuration. They're both happy, but they did different things, folks. I want you guys to carefully take this page down, right? So loss of electrons is oxidation, okay, and gain of electrons is reduction. I want you to take these two reactions down. We're not going to talk too much about them right now because that's a different topic. In a couple of days we'll do that. But in terms of this topic right here, if you lose electrons in general in this topic, to show Leo, we put electrons on the product side. It's very important, but we'll tackle that later. And if we gain electrons in this topic, we put them on the reactant side. Okay, so let's make a note of that in your notes. Okay, guys. Also, I said it before, we'll say it again. We'll take this down, please. Oxidation cannot occur without reduction, so that's why we use this term of redox. And if you look on your reference tables, for example, you look at nitrogen, right, you'll see there's a whole bunch of different oxidation states. The oxidation state is simply an apparent charge, what the charge appears to be when it's combined with something else. So I don't want to get too bogged down with it or too worried about it. We're going to look at some rules of how we figure out what the oxidation state is. Okay, so now we're going to take some notes, all right? So more notes. Okay, and we're going to title it Assigning Oxidation Numbers. Okay, and the thing is, don't want to try to scare you or anything, but if we cannot assign oxidation numbers, our life in this topic is going to be miserable, guys. All right, so we'll get a lot of practice with assigning oxidation numbers before we move into anything else. So I'll give you guys a couple of worksheets to make sure we're okay with it. Now, the first rule, you're going to copy this rule down, please. The oxidation number of any free element is 0. So if you're S8, if you're N2 by yourself, Al by itself, okay, so lone by itself, okay, there's no charge or anything, the oxidation state for each of those guys would be 0. Okay, so uncombined neutral element, oxidation state 0. The second rule, which is also very simple, is if you're a monoatomic ion. Now we know mono means what? Mono means 1, right? And if you're an ion, you must carry some type of charge, right? So here's the deal. If you have this bromide ion right here, Br, okay, this Br -1, right? Okay, his charge will equal his oxidation state, okay? If you're iron +3, okay, or 3 plus, whatever your charge is, that's going to be your oxidation state. So the oxidation state is the same as a charge if you're a monoatomic ion. Okay, so that's 2 rules right there. Okay, so let's move on to number 3. Hydrogen, right? We know for a fact, right, that hydrogen, okay, most of the time will have oxidation state of +1, okay? Now, here's the deal, guys. There's some exceptions, all right? So we know, for example, HCl right here, all right, most compounds, okay, hydrogen is going to be +1. But here's the deal. Let's say we have hydrogen, right, and it's combined with a metal like sodium, all right? Sodium is less electronegative than hydrogen. And there's a rule that we're going to look at in a few seconds. The more electronegative substance or elements will always get the negative charge. So hydrogen can be negative if it's combined with a metal. Like it's just it and a metal, like the metal hydride. Okay, hydrogen will be -1. And over here, guys, the reason why hydrogen is 0 is based on the first rule, right? Because if you're by yourself, uncombined with anything else, you're neutral, and your oxidation state will be 0. Okay, so we're moving on. So we're going on to rule number 4. Okay, now, oxygen is a highly electronegative substance, right? And most of the time, its oxidation state will be what? It will be -2. But there are a few exceptions, guys, okay, where oxygen will not be -2, okay? And here's one of them right here. It's when it's combined, okay, when it's this guy right here. We gotta look on table E now. Look at your reference tables. When it's a peroxide, okay? Now peroxides, you don't have to panic, guys. They're on table E, right? They're just O2 to minus guy right here, all right? When you see that peroxide combined with any group 1 or group 2 elements, right? You know you have a peroxide on your hands. Now, for example, the formula for sodium peroxide will be Na2O2, right? That's the formula for sodium peroxide. You cannot reduce these 2's right here. Why is that? Going back to Chem 1, if you have a polyatomic ion, which this peroxide ion is, you cannot change anything about it, all right? So in peroxides, okay, the oxidation state is -1 for the oxygen, all right? So make a note of that, all right? And in a very rare case where you have oxygen difluoride, OF2, right? Oxygen will be +2. Why is that? Because fluorine is very, very, very what? Very electronegative, and he'll be -1. So oxygen will become +2. But I'll show you how to get a +2 in a second. All right, guys. Winding down. The rule here says if you have binary covalent compounds. Now, what does binary mean? Binary. Bi means two things, right? So if you have compounds, right? Okay, that have just two things in them, and they happen to be what? They happen to be covalent. Now, we know covalent means what? Covalent means non-metals only, right? Now, remember, review your Chem 1 notes, okay? If you have binary covalent compounds, right? The substance or the element that is more electronegative, right? Has more electronegative, that substance will get the what? Will get the negative oxidation state. Now, you're probably wondering, where am I getting these numbers from, right? You simply look on your periodic tables, people. So that's when I ask you guys to look at your periodic tables. Because if you look for F, right, on the top right corner, you'll see it's -1, see a little -1 there. So that's going to be the oxidation state for fluorine, for example. Okay. Now, chlorine, right? Okay, once again, you look at the oxidation states, you'll see a -1 for the chlorine at the top. You will use that if it's combined with something that's less electronegative. Okay, alrighty. Now, last one, okay, for number 6. For any neutral compound is important. If the compound is neutral, the sum of the oxidation numbers must equal to 0. Now, how do you know a compound is neutral? For example, I got here CO2, right? Now, carbon dioxide, you don't see any charges anywhere, right? Just regular CO2, right? That's a neutral compound. So what I'm trying to say is when I add up the oxidation numbers for these two oxygens and this one carbon, they all have to add up to 0. Okay. Now, if you look on your reference table, oxygen is what? Oxygen is -2. Okay. So what's 2 times -2, folks? 2 times -2 is -4, right? So what plus -4 gives you 0? +4, okay? So carbon will be +4 and oxygen will be -2 in terms of oxidation states. Now, if you don't understand what I just said there or calculated there, don't worry. I have a whole video on how you calculate the oxidation states. What I want to do today is just go over the basic rules with you. And for 6B right here, people, if you have a polyatomic ion, for example, the guy's on table E, right? When you add up, okay, when you add up their oxidation numbers, these 4 oxygens and this 1 phosphorus, they have to equal whatever the charge of that ion is. So in this case, the charge of the ion is what? -3, right? So when they add up when they add up the phosphoruses and the 4 oxygens, they all have to add up to what? To -3. How do I know? Because this is the charge right here of the polyatomic ion. Now remember, guys, once again, I'm going to give you guys a video on how to do the actual calculations, but please take down the rules of all these things. Now, ladies and gentlemen, now's a perfect time to do what? Now's a perfect time to review your Chem 1 notes. I have also Chem 1 stuff, okay, on my site right here. I'm up to this number of views, okay, so I'm pretty happy about that. Okay, and subscribers, and see you guys later. But on a serious note, people, please be safe. This is a very, very, very trying and tough time right now, but we'll get through this. As always, hard work plus sacrifice equals success. Take these rules down, take the definitions down, Leo Gurr, and all that stuff, and I'll send you guys a video later on how to do the actual calculations of oxidation numbers. Take care.